All right, I'd like to finish up what we did on minimum spanning trees, which kind of gets us started with graph algorithms. We'll shift over to the ABCs of graph algorithms, breadth first search and depth first search, which are not so much useful in and of themselves, more that they're useful as tools in other algorithms. And then we'll end off with the shortest path algorithms, which are perhaps the most famous of all the graph algorithms. And there's different versions of the shortest path algorithms in the little frontier of which versions are NP complete and which aren't. There are plenty of other graph algorithms, in particular maximum flow, or min-cut, it's the same thing, and matching algorithms. Algorithms that have to do with pairing up edges and getting as many pairs as you can in a graph. And those are much harder to explain, and we just don't have the time in an introductory course, but they're well worth looking at, and we could have advanced recitations on them. But they're deep topics in and of themselves. You should know, at least for those algorithms, the standard easy explanation of them is n cubed. So everybody always asks me, well, are all these algorithms always like linear time or n squared? And no, I mean, those are very practical algorithms, and the first version you'll learn will be n cubed, and it's pretty intense just to get it down to n cubed. All right, before we get started back with minimum spanning tree, I want to give you some examples of minimum spanning tree-like problems that are NP complete, that aren't easy to do. And one of them is a question Todd asked me at the end of class, and I had remembered something like it, but I wasn't quite sure of the particular version he asked me, and I went to check it right after class, and indeed, it's a hard problem. It's an NP complete problem. And it's not a hard question to describe. His question was, what if I had this graph that we start with, but instead of finding the minimum spanning tree, I want to find the tree that minimizes the length of the paths between all the pairs of nodes. So I come up with a tree, and I take every pair of nodes. You know, in a tree, there's only one path between every pair of nodes. You don't have any choice. So you calculate all those paths between every two pairs. You add them up. That gives you the distance, say, of that spanning tree. And it represents the idea that after the town's been flooded and you repave it, you want everybody to have the smallest hike between the sum of the collective kindness to the people in town. The sum of all their walks should be minimum. All right, so can you find a tree that minimizes the sum of all the distances between every pair of nodes? And the answer is you can, but it's NP complete. So the best anybody knows how to do is an exponential time algorithm, meaning the best anybody really knows how to do is probably try all the spanning trees, something in the order of 4 to the n. The similar problem of just trying to minimize, say, the longest path, the longest any two people have to walk from one to another's house, not the sum, but just you care about two important people, that's also NP complete. Another version of minimum spanning tree that's NP complete. If I give you a graph and I say, find me the minimum spanning tree that just includes this particular subset of nodes, that's hard. You know, when I don't say it has to span everything. Here's a geometric version that's hard. Somebody gives you a bunch of points, not a graph anymore, just a bunch of points on the blackboard, like these 3. Now, if I just asked you what's the best spanning tree, the minimum spanning tree of these 3, you could do it with a normal algorithm. We would just imagine that all the edges were there, and we would do the normal minimum spanning tree algorithm. But this version allows you to find the minimum spanning tree for these 3 points, but you're allowed to add extra points. You're allowed to go into town and create a new intersection instead of just connecting the old houses. So if I didn't do that, the best we could do here, this is an equilateral triangle, is just pick 2 of the edges. Right? Does anybody happen to know what the actual minimum spanning tree to connect these 3 points is, if I can add extra intersections? This is the best. The sum of these 3 turns out to be smaller than the sum of those 2. Now, this is a hard problem. It's a hard problem to take a general collection of points and decide what's the best way to choose a whole bunch of other points so that when I connect them all up, the edges are minimum. That's also NP complete. This is called geometric Steiner tree. And it relates a little bit to a problem that Rob mentioned at the very beginning of the course, this penny problem of arranging pennies in such a way to minimize distances between their centers. And it's related to that. So I want you to realize that minimum spanning tree has plenty of similar sounding variations that are still quite difficult. You can't really get a handle on them at all. But the regular variation is really easy. There's Todd's bike wheel that he fixed this morning on the way to work. Here's the length of all the spokes. What's that?
What's the least I can fix?
Right. So Todd's wheel completely fell apart, and he needs to reconnect the spokes so that he can ride to school on a spanning wheel. Interesting. Here's a graph. We want to get a spanning tree out of this graph. We're using Kruskal's algorithm this time, not Prim's algorithm. The good news is that Kruskal's algorithm is much easier to implement, and it introduces a really cool data structure which isn't that complicated to describe, but whose neat features are really just built up on some cool math. And we don't have to get into too much of the hairy details of the math. So you'll be able to really understand all this without too much energy and compartmentalize the hard part to look at later. The way Kruskal's algorithm works, let's not talk about implementation yet, but just review, is that it does the edges from smallest to largest, but it doesn't insist that the new edge has to connect to the tree that's already growing. The trees can grow up in parallel like a forest and then connect as they go. So basically all it's going to do is try the edges in shortest to longest order, and if it gets an edge that actually makes a cycle, it's not going to try that. It'll just discard that and go to the next one. Let's see what happens. So it starts off picking an edge of length 1. Any of them are okay. Just whichever one it comes to in the graph structure first. So let's say it's doing things alphabetical order in the graph structure. So it might hit this edge first. All right, that's 1. Then it might go to, well, let's say E comes next in the structure. I'm switching it around. It might go there. Then it might go here. Now what are the choices? This or this. Let's go to this one. So now we have three trees, neither kind of semi-spanning trees, and they're going to start connecting. Now this connects it. Now if we choose one of the two edges, we're not going to pick this one because it creates a cycle. Right? We're not going to pick that one because it creates a cycle. We won't pick this one because it creates a cycle. But we will pick this one because it doesn't create a cycle. It connects two of the trees that are already there. So this one gets connected. And now we go on to the rest of the edges, the 3s. And I think every one of the 3s creates a cycle. There's no more edges to check, and we're done. OK? That's it. That's the idea. Let's talk about implementing this, but before I do, any questions first about how it works? Okay.
So 1, 2, and 3 are the lengths?
Yeah, well, they could be any numbers. I just used 1, 2, and 3 here.
But it's the lengths of the process.
Yes, the lengths of the, yes.
The only thing, you just have to consider the weights and no cycles, and that's it.
That's it. Right, I know. The other one has heaps and it's a lot easier. Well, you'll see. Is it a lot easier? How do we implement this? What do we have to do? We got to go through the edges from smallest to largest. So what's a good way to do that? Let's take all the edges and we'll sort them. We'll do that at the beginning. So step 1, sort the edges. How long does that take? Let's analyze it as we go. E log E. Now, E can be at most n squared. So this is like n squared log n squared in the worst case. And log of n squared is 2 log n. Right? So this is the same as E log n. Log e is the same as log n as far as big theta goes, because e is n squared and log of n squared is 2 log n. Okay? Log of something squared is a constant factor of the log of the variable that's been squared. So these two are the same, and this is as good as Prim's algorithm worked. So far we haven't used any more time than Prim's algorithm, and we're okay. All right, questions so far? All right, next step. Step 2 is going to be a loop. We're going to go through this list of sorted edges in order from smallest to biggest, and we're going to try to add them into our tree. So let's consider an edge. Let's say we consider an edge xy. We're going to have to figure out a way of asking ourselves the following question. Does xy make a cycle in the tree we have so far? Right? There's a lot of ways to try to do this. This is a big, open question. I could send you back on a problem set and you could work for a few hours deciding the best way to store your data so you could ask the question, store the tree, and ask the question whether a new edge creates a cycle in that tree. But there is a very, very nice implementation that I'll suggest that has become kind of standard. And here's what it is, and it really builds on a data structure that's useful in a lot of other problems. So here's what we're going to do. Let's go back to the beginning of this problem. At the beginning, we're going to imagine that we have A, B, C, D, E, F, G, A, B, C, D, E, F, G, all sitting around like this. In other words, 7 separate subtrees. And every time we get an edge, say AB at the beginning, we look up and we see, are A and B in the same group, or are they not in the same group? Or are they in the same set, or are they not in the same set? We have 7 different sets here. What we need to be able to do is store sets of things and check, given a particular pair of things, whether they're in the same set or not. All right? So right now we'd have 7. So this data structure is sometimes called, it's got a funny name, so I'll explain why in a second. It's sometimes called a union-find data structure because it has to support finding something. If I give it, say the picture looks like this. Say these are in one set and these are in the other. So I have 2 sets, and I come up with the edge AG. I got to be able to know, given G, that I'm talking about set 2, and given A, that I'm talking about set 1. I got to have a way to find what set my element is in. That's the find part of this data structure. So the find part takes a value that's going to be in one of these sets and tells me what set it's in. The union part is when I combine these two together. Because if there is an edge, A to G, I'd like to make these into one set, so that from then on, they're all considered one group of elements. Everybody get the union and the find part? If I can do both those things, I will keep track of exactly what trees exist. Every little subtree will have its own little group of nodes in its own little set. In mathematics, these are sometimes called equivalence classes. Each one of these is an equivalence class, and the nodes inside it are all, quote, equivalent one to another. And we're merging equivalence classes in this problem from 7 separate equivalence classes to one equivalence class where they'll all be together in one spanning tree. Right? That's the connection back to discrete math. But you could also just think of it as disjoint sets that are getting unioned together. All right, that's the big picture. We'll talk about the details in just a second. Are there questions so far? So let's look at what actually happens in this algorithm. The way we did it, we had all these 7 in different sets, all on their own. And then the first thing we did was look at the edge AB, and we ask ourselves, where's A? Well, A is over here, and where's B? B is over here. They're in different sets, so now we're going to combine them into one set. And we go on. The next edge we chose was EG. E's here, G's here. They're in different sets, so we combine them. So now I have 1, 2, 3, 4, 5 different sets. And then I did DF. So I combine these. Now I've got 1, 2, 3, 4 different sets. And then I did CD, I think, right? C is by itself here in this set. D I have to find. It's in this set. And since they're in different sets, I union them together. So now C is included in this set. And then I went over to try, well, first I went over to try something that didn't work, right?
You tried it.
Oh, first I have to do BC, right. So now these guys are connected too. So now I've got two big sets, A, B, C, D, F, and E, G. If I do find C, it should tell me set 1. If I do find G, it should tell me set 2. And now I came up with an edge A, D, a 2-edge. And I find A and I find D, and they're in the same set. So I don't do anything, I don't merge anything, I don't union anything, I skip it. Being able to tell what set a particular element is allows me to answer the question, does X, Y make a cycle? If X and Y are in the same set, then the edge would make a cycle. If they're in different sets, then the edge does not make a cycle. Okay, questions about that? This data structure is useful in a lot of problems where you need to do just this kind of merging of disjoint sets. And in this problem, it's extremely useful. What we're going to do now is see how we're going to implement it. But before we do, get the details underneath the scenes, let's finish describing the algorithm. So if x, y, let's actually write it with the data structures. If find x equals find y, what does that mean, if find x equals find y, given an edge x, y? That means they're in the same set. What do you want to do? Don't do anything. So I'll say if not. If they're in different sets, then what do I want to do? Then union find x and find y. So now they're together in a big set. Practically speaking, you probably wouldn't call these twice. You'd call it once at the beginning, w equal find x, u equal find y, and then use w and u there. I mean, details like that, for efficiency, you can work out yourself. And this is going to be in a loop for each x, y in sorted order. That's more or less the algorithm. Now, every time you do a union, that edge gets put in the spanning tree, right? When we're done with this, all we've done is gone through the whole algorithm, and we haven't kept track of the edges. So somewhere in here, we should maybe store x, y somewhere, or output it, or do something with it. That's an edge that's in the spanning tree. Okay? So that's where the output comes out. That's more or less how the algorithm works. Now what we have to do is talk about how to do find and union. Okay, questions? Yeah, John.
I haven't caught how this is finding the shortest path yet. You're cycling through, you've sorted all the edges, so you've got all the ones at the front.
Right.
How do you know when to stop?
Oh, when we're done with looking at every edge. We look at every edge once.
Yeah.
We can short circuit it, I imagine, if we only have one set left.
Yeah, that's what I was...
Oh, sure. You could stop when you get one set, but it doesn't take so long just to go through every edge once.
Right.
Let's analyze how long this takes. I mean, this loop is E long. So the complexity for this loop is E times whatever time it takes to do these finds and unions. And we don't know that yet. So if that's going to be log n, then we'll be OK. And it might help constant factor-wise to stop it early, but it's not going to matter in the complexity of the algorithm. But sure, you could stop it earlier if that's what you're thinking. Absolutely. Other questions?
And are you proving that this is the shortest path, the shortest tree?
Well, I'm not going to prove it, but it's true. And There's a theorem that basically says if you have two separate trees, then the shortest spanning tree overall is the connection of those two with the smallest edge between them. And then you can use that inductively to show that this gives you the minimum spanning tree. So there is a theorem. I'm not going to prove it, but it's true that this works. Okay. How do we do union and find? There's a lot of different ways to implement this. You can try to do it with all sorts of different structures. But there's one way that works out really cool. And I'll show you what it looks like. The first thing we do, and I didn't write it down in this algorithm, but it should be kind of apparent. Before you start the algorithm, you have to start out with 7 distinct trees, or n distinct trees, for every node. Right? So you, besides being able to union and find, you also need initialize set, or make set. So at the beginning, you make these 7 separate sets. And the way we're going to store them is each one is going to be stored with its own array. Every set will be stored with an array, and the array will be a parent array, just like we used in the algorithm we did yesterday. So right now, it's going to be 7 different arrays that store the value A through G, and all their parents are nil. These are all roots of their own tree. We're going to store each set as a tree and represent the tree as a parent array. Okay, so this is going to be parent of A is nil, parent of B is nil, etc. 7 different sets. Whenever we merge or union 2 of the sets, here's how we do it. A and B, for example, we take A and B, and we point the parent of one to the other. If you have 2 trees, and you want to merge them, take the root of one and point its parent to the root of the other. That's all you do.
Which direction we point
it will matter, but right now it's just arbitrary. Right now, just make sure you point one to the other. So let's say we just pointed B to A. This is what it looks like now. In the array, parent of A is nil, and now parent of B equals A. It's just an array behind the scenes that stores parent pointers and shows how to keep things together. All right, let's do the next step. What did we merge next? D and F, was that right?
E and G.
OK, but we'll do E and G right here. And then we connected C and D. That means C and D. Here's C. Here's the D set. What's the root of the D tree? It's D. And the root of the C tree is C. We're going to connect them. We can either connect the D to the C or the C to the D. So here's what we got. A set of AB, a set of CDF, and a set of EG. That's what we do. Parent arrays, the parent pointers move around to connect different sets. Let's stop for a second. Who has a question about this?
When you're saying parent arrays, there's only one. There's one array with a pointer.
Yes. 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 Good question, Michael. Right. There's one big parent array, but inside it, we think of there being lots of different trees because if you followed these parents back, they wouldn't all connect to one another at the beginning.
Right, but they're just pointing back into other cells in the same array.
That's correct. There's one big array called the parent array, and they start connecting back and forth to each other, merging and merging as you go. Yes, yes. That's a good question. I should have been more clear.
So, I'm
Yes,
sorry.
sure. Yep.
Now I'm a little confused. We initialize 7 arrays when we start out, or we initialize
7 slots in one array. So it looks like this. You have A, B, C, D, E, F, G. And they're all pointing to nil at the beginning. And then after the first step, we point B's parent to A. We point D's parent to C. we point F's parent to D, and then we pointed D's parent now. I did it backwards. F's parent to D, and then D's parent to C. So now that's what it looks like here, and then we still have to do G's parent to E. So that's what it looks like in this picture.
What value are you using for those pointers? Are you using like an integer, or are you using the location in the array? Or
The index of the array, typically.
Okay.
Here the indices are letters, but yeah, you'd use the number index in the array. OK. Let's go back to thinking about these things. How long does it take to do make set, to create a set? How long does it take to create a set?
One step.
Well, all of them takes n. But to create a single set takes 1 step. OK, so to do all of these initializations at the beginning just takes n time. That's no big deal. OK, so the initializing takes order n. How long does it take to find an element? How do we represent one of these sets? Basically, each set is represented by its root. If I asked, where is F, you should tell me it's in the tree of C. Where is G? It's in E. Where is C? C is in C. Where is B? It's in A. Where is A? It's in A. Every one of these sets is represented by its root. We have to have a way of calling these sets. Instead of giving them all new names and changing their names all the time, we simply call the set the name of whatever happens to be the root. So how long will it take us to find the name of a set once we're given an element in that set? We have to go to the array. For example, if I ask, where's F? We look at the parent. The parent's D. What's the parent of that? C. What's the parent of that? Nil. Parent of that's nil. So the second we get to that top, we say stop. And we're in set C. OK? How long does that take? What's the worst case? N, because this tree can get really thin and long. Right? So I'll write right now, without doing anything clever, find, a single find could take order n. What about a single union? How long does that take? Once you found something. It takes 1 step, right? You found it, you know its root. You found the other one, you know its root. You point the parent of this to this, 1 step. So unions are fast, finds are lousy. Let's analyze our algorithm, assuming finds take linear time. This is a loop of size e. Linear time every time through it. That's e times n. That's too slow. Okay, Prims did it e log n. We got to do better than en. We got to get the find down. OK, questions so far? So now we're really talking about data structures and not so much this algorithm anymore. We got to figure out a way to make the finds faster. Yeah, Chris.
That's my question.
OK.
Why is it en? Because step 2 is n, and step
Because every find here takes n time in the worst case.
Right.
And we're going to go through this loop e times for every single edge. So e times n. All right. When you get 2 trees like this, or 2 sets like this, and you want to union them together, Doug asked me before, is it random, whether you point one root to the other or this root to here? And I said, well, not really, but right now assume it's random. So now we're going to go back and assume it's not random. What's a better way to do it? Would you like to point here to here, or would you like to point this to this?
Second.
The second to the first, because it keeps the tree bushy and balanced. It doesn't keep it skinny. So if we add the following, we'll call it a heuristic, because it's just a good rule of thumb. If we add the following thing, and it only takes 1 extra if statement to check, all we got to do is check, is the height of this tree bigger or smaller than the height of this tree? And connect the one with smaller height to the one with bigger height. Now, it may be hard to believe, but that simple little if statement to decide which way to do the root is enough to guarantee that in the worst case, union turns into log n. And the
Fine.
yes. Right. That good trick just made union even worse than it was before. So this is with, we call it weighted union. All you got to do is look at the number of, at the height of the nodes in one side of the tree and the height in the other, and do it in the right direction. It's not too hard to keep track of the height. You can just keep it sitting in the root node, or keep it in a separate place, heights, and every time you add one, you can just modify it. It's not a big deal to do that. So it doesn't cost us anything extra, but it saves us a huge factor in the long run. And the proof of it is by induction, that if you always go for the smaller height to connect up to the root, the thing stays as balanced as possible. Never gets out of whack. Well, that's really nice. And once we've done that, now our algorithm has turned into E times what? E log n, and that means it's the same as prims asymptotically. All right, but we're not done yet. We're almost done. There's one souped-up version of this data structure that is really hard to analyze. I mean, this proof you could all read through and understand. But the next version is something that really would take a couple of lectures, a very intense study to understand. But I will give you the result because it's really cool. We're going to add one more little feature to this algorithm, and it connects to something that requires an amortized analysis, which we'll talk about later in a simpler context. But here's what we're going to do.
Actually,
Yeah.
I've got a question before we move on. Is there any reason why we, in this case, have to make it a binary tree? Why we couldn't just have every single one point to...
It's not a binary tree.
Well, we've got two that are pointing into the same parent.
You could have three pointing into the same parent. Sure, sure.
So then
It could definitely look like this. Sure, it could look like this.
okay, so there really should be no reason we should have anything with two extensions. Like that, the one on the left.
Well, but how do you guarantee that? Let's say it looks like this right now, and we have to merge these two. So we're going to point this to here or this to here. Whichever way we do it, we're not going to be able to keep it just one depth. So we'd like to be able to do that, and actually Doug's kind of, again, hitting just the right idea to help us, because we would like to keep it as bushy as possible. Yeah?
How would we ever get to that, the one where there's two, if you were always just adding it to the root?
Here we added it to the root. Here we have a new one. You want to add that to the root. Here we have ones like this. And now what do? Now you got to add this one to here or this one to here, and that puts you down a level. It's a good question, because maybe by induction, if we just assumed they were always one level deep, we could keep them one level deep. But the inductive glue doesn't work. When you have two things that are one level deep and you connect one root to the other, you get something that's going to be two levels deep.
Because it all goes, it's all connected to the same one. With Prim's algorithm, you start in one place and you just keep going.
Right. Well,
I mean, you wouldn't do
with
it.
him, you never have to union anything at all. Right. 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 All right. But we would ideally like to keep this more bushy. So here's another trick. And this heuristic is really cool, because the analysis doesn't actually come up with anything until you actually do it a little bit and see that it works well. But here it is. It says this. Let's say you have something that looks like this. Let's make an example up. And this is, say, vertex x, and you got to find x. Normally when we got to find x, we just pop up. We say, here's the set. We're done. Here's the extra heuristic. It says every time you do a find and you're moving up, what should you do as you move up? Yeah, take it with you, right. As you move up, take every one of these pointers as you traverse them and set them up to the root. So you're going to, when you're all done here, if I call this x, y, and z, here's what it's going to look like when you're all done. X and y are going to be here and here. Every time we do a find, we'll just make sure we keep the tree really, really bushy. Now, it doesn't seem like you're going to be able to get a handle on why this really helps, but you should get a sense that, oh, it's got to be helpful because we are at least keeping this nice and small. Maybe even less than log n. Maybe even constant. So it turns out it doesn't get to be constant, and in the worst case, it still is log n. You can come up with a pathological example that even if you get all the perfect finds you want, I can come up with an example where the length of a path stays log n, in the worst case. But it turns out that if you look at a whole algorithm from beginning to end and check all the different unions that might occur, that you only get the worst case coming up very infrequently. The log n hardly ever comes up. So if you take it over many, many uses of this algorithm, many, many uses of the finds and the unions, it turns out that although the worst case for a union is log n, the worst case for p unions is not p log n. The worst case for a lot of unions is much, much, much less than p log n. All right, so let me write this down. This is called path compression.
What's the cost of that going to be? Is that just going to be like
It doesn't hurt at all. It's an extra constant step while we do the find.
Okay.
So it makes our find was order log n, now it's 2 log n. It doesn't affect the complexity at all. So the worst case with path compression is still order log n for a find. That's the worst case. But the worst case for p finds, if you're going to do a lot of finds, is not p log n. It's better. It's a lot better. That's what amortized analysis is about. The worst case is bad, but if you do lots and lots of these, the worst case never comes up that many times in a row. Having the worst case show up helps you for later. It's like you invest in the stock market every year, and you're a random investor. You're not so good, you're not so bad. The worst case is you got a bad year and you lose 60% of your money. But if you keep your money in for 30 years, you don't get that worst case showing up every single year. You'd say over 10 years, I'm expecting to gain 10%. And that's kind of what's going on here. The worst case is going to cost you log n. But I guarantee that if you do it a lot and average over all those different times, it's not going to be log n. I can prove to you that it's going to be better. And here's what it turns out to be. P finds turns out to be P, we'll call it log star n. Log star n is a function that's teeny, teeny, teeny compared to log n. Log star n is that function I introduced to you yesterday. If I give you a number with a stack of 2's on it, log star of that number is the height of the stack of 2's. So log star of 64,000 is 4. Log star of any normal number in the universe is 5 or less. Right? So it's an incredibly slow-growing function. You can put any size graph in the universe in here, and this would be 5 steps at the worst. So over the long run, if you do p finds, they're really taking 5 steps each, at the most, not log n. That's a really cool result. And all you have to do in order to get that nice result is take these vertices as you go up and point them to the root. Okay, let's say we use path compression. Let's analyze how fast this step takes. We go through a loop e times. Every time through that loop, we do a couple of finds. Over e finds, how long do we expect that to take? According to this, e log star n, or essentially e. So this e log n step just got knocked down to e because of this nice amortized rule. Because when we're doing lots of these finds, they never add up to e log n worst case. One might be log n, but when you're doing lots of them, that's not going to happen. It's noticing that interesting fact that the worst case doesn't show up when you do something over and over again. That's what amortized analysis is about. Yep.
This isn't even just an average case analysis. It's the fact that we could not design a pathological data set that would over a number of finds give us log n.
That's right. That's right. It's different than average analysis, but it's very close to it. And what you said is exactly right. That's right. You can't design an example where over p finds you do worse than this. That's true. Yeah. Sharon, what are you thinking? What's your question? Looks like you got a question. No question? Okay.
So this is only for step 2, though, right?
Right.
We're still E log.
Good. So the whole algorithm still takes e log n because of this. So maybe now there's a way to do this a little bit faster and get the whole algorithm down. But you're right, Michael. This only improved the second step. Questions?
So this whole thing is done just with an array.
The only data structure here is the original graph and then an array. Right. And the graph needs to be adjacency lists so you can go through the linked lists and pull out the edges without using n squared, using e time instead of n squared. Other questions?
Why is the second method called a weighted union?
Just to distinguish it from the regular union. If you do a regular union, then finds are very slow. But a weighted union means you're going to make sure that the smaller one gets rooted up to the bigger one. So you're counting in the weights in some sense.
So that's how you decide. You're just counting the number of nodes in each tree and whichever one has
The height.
No, actually, I was a little fuzzy about this. I said height because that's the one that makes sense. But in fact, it might actually be a little bit harder to calculate the heights of these trees than it would to calculate the actual number of nodes in the tree. And it turns out any way you go works out. But ideally, just think of it as the heights. But yeah, whether you do heights or weights, it would still work, I think. And one might be a little easier to implement than the other. But I think it's pretty clear to see with heights that it works. Other questions? All right, so this finishes minimum spanning tree, but it introduced this idea of amortized analysis, which I only got to explain to you in this very fuzzy, intuitive way. And I want to nail it down with a real particular example that doesn't use graphs.
Were we going to look for a better way to sort the edges to make that?
No.
Okay. I thought you were leaning there and then.
No, I was leaning there, but there's only... No, we're not. In using a stacked data structure, you have to do push and pop. How many steps does each of these take? What's the complexity of a push? What's the complexity of a pop? 1 step each. That's pretty darn fast. We're not going to do much better than that. All right. Now let's say I'm implementing my stack with an array. And say the array has, 10 things in it. What happens when I get up and I fill it with 10 things and then I do another push? What happens in your programs? It'll say error, your stack is full. Let's say I wanted to make a fancy data structure called I never get full stack. And when you push into a full stack, what it does is give you some more space. Okay, now it's an array, so it's going to have to allocate a bunch of space. And it's going to have to use some time to do that. So here's one method of doing that. One method of doing that is I got 10 spaces right now that the compiler gave me. I need a new area that has more space. The compiler cannot necessarily just give you the next slot because it might have given that memory to somebody else. So what you're going to have to do, you're going to say, compiler, give me more room. It'll give you more room, but you're going to have to take all your numbers that were in your array and move them over to that other room. So you say, give me 20. It'll give you 20, but you got to copy those 10 that you had in this place over to the new array that it gave you. And that takes a lot of time. That takes your push and turns it from an order 1 into an order n.
Do we just use a pointer to the new location?
Sorry?
Use a pointer to the new location so when we get to the top of the stack, run out of space, the last one is a pointer to the new location. We don't have to copy everything.
You could do that.
Okay.
You could do that. But it won't let me explain this nice analysis. All right, so assuming we want to free this old place. Let's say that. Whatever. Make up a reason why you wouldn't do that, and let's continue. So this starts getting slow. But the point is, there's a way to implement this where this slowness can't possibly happen every time. And over many, many, many pushes, the slowness never happens over the long run. I can prove to you that if you do, say, k pushes, it's not going to be kn worst case, but instead it's going to be 3k worst case. That this is really like order 1 and not like order n. But we have to do it in the right way. So here's what we'll do. We'll start out with an array of size 1, and when we use it up, we double it. We get an array of size 2. When we use up the array of size 2, we double it. Turns into size 4. When we use up the array of size 4, we double it. We always ask for double the space we had before, and when necessary, we do copy over the values. Okay so far?
Yeah, but
Yeah.
we start with a higher value.
Yeah, practically you'd start with whatever, 50, and you'd double that. But we're going to do an example with 1 because it will still give you the idea. Yeah, so let's see what happens. Let's count. Let's say we do a whole bunch of pushes. Let's count how many steps it takes. The first push takes 1 step. Now you're ready to do another push. What happens? We have to copy over. Right? So the first copying, I'll write the copying spots, happen when we're adding in the second element. Okay, and here we'll see how many steps it takes. How many steps does it take to do the copying when you add in the second one?
1 plus the push.
1 plus the push. But the copying itself just took 1. Okay? When's the next time we're going to have to do a copy? When we're adding in the... Well, the third. Right? We only have a stack of size 2 now. So when we add in the third, we have to copy. And that copying takes 2. When we add in the
Fourth, we have 0. You don't have to copy.
So when do you have to copy next? And how many steps does that take? When's the next time you have to copy? And that takes... All right, let's stop there for a minute. That's enough to give us an idea. We've now pushed how many times? We've pushed 9 different elements in. This represents how many steps our copying took along the way. And in addition to this, we've also pushed on 9 elements. So we have all this stuff plus 9 for our total amount of work. Let's add it all up. 1 plus 2 plus 4 plus 8 plus 9. 12, 14, 15, 9, 24. Exactly 3 times 8, the number before this. Now, is that an accident or is it not an accident? Sam yelled out 3n, so it's probably not an accident. And let's analyze and make sure that it's not an accident. What happens when you go down here and you add all these numbers up? 1 plus 2 plus 4 plus 8.
2 to the n plus 1 minus.
It's going to be 2 times 8 minus 1. Right? This is like a binary tree. It almost adds up to 8, but just misses it. So this whole thing adds up to 2 times 8 minus 1. And how many pushes did we get to require these copying? 8 plus 1. Now I could have done this analysis with 2 to the n here and with n. It would have been the same thing. 2 times 8, 3 times 8, plus 1 minus 1. 2 times n, 3 times n, plus 1 minus 1. When you do this analysis and you do k different pushes in a row, it takes 3k steps. Even though the worst case for a single push is the size of your stack, the worst case for k pushes is 3 times k, not n times k, not the size of your stack times k. So this is the best specific example of amortized analysis that I can show you, where the worst case for a push takes n, but if you put lots of pushes together, you don't get kn, you get 3 times k. The way that some people like to think of this is the following. Sometimes these pushes are expensive, and sometimes they're cheap. They're expensive when I have to do the copying. They're cheap when I don't have to do the copying. I want to kind of convince you that over the long term, you're going to save money. You're not going to spend so much. So here's what I do. On the cheap days, where it costs you 1, you're going to put 2 pennies in the bank, or 2 steps in the bank for later. So every time it costs you 1 step, and you don't have to do any copying, give me 2 for free so I can save it. And I put that in the bank. That means it's really costing you 3 steps, but 2 are for saving and 1 is for actually doing it. And then when I finally have to do something really, really complicated, like copy, I can use those steps that you saved up in the bank. And if I can work this accounting carefully, I can show you that saving 2 steps on the bank for every time you have an easy push is enough to take care of those bad years when you have the really expensive push. And that's why it's called amortized, because you spread out the cost of your big expense over the very, very small costs over the years, or over the multiple tries. All right, so this is a sense of amortized analysis, and that's the flavor of which will give you the sense of the result that I just told you for minimum spanning tree. All right, that's all I'll do on this right now. Are there questions about this? All right. Blake, you had a question? Yeah, Doug, question?
Yeah, do we completely neglect in the amortized analysis that when we pop something, it's going to free up some space?
Well, that only helps us, and normally we wouldn't. In fact, you can also do this, you can extend this, and say, you can do a special thing for pops as well, and extend this idea. But whatever argument I just gave you works true for collections of pushes and pops. If I have a collection of k pushes and pops, I'm never going to do more than 3k steps, because the pops are always 1. So the pops only help us, because they're never expensive. But you could even make them expensive in certain circumstances and still amortize it, and it would still be okay.
So we would never, doing amortized analysis, we would never decide, well, maybe there's going to be a certain percentage of the time you're going to pop, and so we can lower the cost of the pushes.
Oh, whether it's, yeah, but I guess once you get to linear times k, you're happy anyway. Okay. So we're not going to worry so much whether it can get to be 2.8 times k. As long as we can get it linear, we're all right.
If your stack is implemented with an array, pushing and popping actually linear, you have to shift everything?
No, you don't shift everything. You just grow.
You have pointers to the top of the array. Okay. Increment that.
Right. You keep a pointer to the top of the array. You move from there. You move down from there. The only issue is when you run out of space, you got to get rid of that space and get new space. Yeah. But you certainly don't search through the array to find the top of the stack. That'd be too slow. You're right. New topic. We're talking about breadth first search, depth first search. We're leaving minimum spanning tree behind, union find behind, amortized analysis behind, new ideas. BFS over here. DFS over here. The difference conceptually between breadth first search and depth first search is very straightforward. They both go through a graph and process each node at least once, but they do it in a different order. The question is what they're going to do as they go through and process each node, and sometimes they can do very complicated things. For now, all we're going to ask it to do is go through and print out the nodes, for example. So in this case, the way breadth first search works is it starts at the top and goes a level at a time. First it would print out A, then it would print out B, C, and D. Then it would print out all the things that those connect to, namely E and F. It would do it a level at a time, going breadth first. How do you actually implement this? The data structure that goes with breadth first search is a queue. The data structure that goes with depth first search is a stack. There's a really natural way to implement this, and you should imagine that your graph is stored with a normal data structure, and we use a queue to help get these nodes out in the breadth first order. And here's how you do it. Here's your queue. You take the node that you're starting with in your graph, and you throw that in your queue. And now you run a loop that says this. While the queue's not empty, take that node off the queue, look at all its children, and put them on the queue. That's it. While the queue's not empty, take this off the queue and put its children on the queue. What happens? A is taken off the queue. You look through the graph data structure. A is connected to B, C, and D. So B, C, and D go on the queue. And now you continue. You look at B. That's the next one to get sent off the queue. The order that they're sent off the queue is the order of breadth first search. B goes off. What are B's children? Ooh, what happens then? Right, so we need to have some kind of array, and this is in both breadth first search and depth first search, called a marked array, or in the queue array, or I already have seen you array, something that says, I already saw this node, don't look at it again. Typically it's called a mark array. So we wouldn't put D on the queue again, because we've seen it. So we skip that, and then we are now done with B.
The ordering of B, C, and D is arbitrary?
It's arbitrary. It depends on your data structure and what the order of your linked list is. But it's arbitrary, yes.
So the marked array, I'm kind of curious what type of structure we would have for that would be easy to access.
Just a static array of sized nodes in the graph.
Okay.
And you set it to 0, 1, a Boolean array. Sometimes we might want to actually store numbers in it because we might hit these in a particular order. And we could do that. Instead of storing a 1, we'd store whatever number was next. We'd increment instead of just hitting 1s. But we could either store numbers, the order that we found these nodes, or we could store just a 1 for being marked. If we stored numbers, then A would have a 1, B would have a 2, C would have a 3. And all the rest would have zeros because we haven't seen them yet. Yep.
This works in the game that we did. Is that the same thing?
It certainly works. You could do this idea in that game that you did. You could also use a depth first search in the game that you did. This is useful for any kind of processing where you're going to go through the graph, look at a node, and do one thing, and then move on and look at the node, look at the next node. Depth first search, I must say, has many, many more applications because of its recursive structure. There is nothing recursive about this. This is iterative. It uses a queue to run through it, and it has some applications, but nowhere near as many as depth first search. The key thing about depth first search is that it starts going down first. So when it backs its way up, it's got so much information that when it finally backs its way up to the node that called it, that node that called it has tons of information it can use to process and make decisions. That's very vague, but you will see some really cool stuff that depth first search can do that breadth first search can't. Okay, there are some basic things they both can do, but a lot of things that one can and the other can't.
Breadth first search has this call sibling. There's all this hopping to siblings. That's not a native operation in these trees either, is it?
No, sure it is. We have a graph that stores this. So the graph looks like this, Chris. A, B, C, D, E, F. And A connects to B, C, and D. It looks like something like this. So when you throw A in the queue and then you take it off, you just look through this linked list at its children and you chuck them on the queue.
I was thinking of it as a tree rather than a...
Oh, if you think of it as a tree, no, it's not a tree. It's a graph. And that's why we store a graph this way, is to make things like this easy to do. Yeah. Other questions? OK. There's a lot of uses for breadth first search, but not as many as depth. What's one quick use? Well, no, I'm pausing. You're going to see a really nice use of this in the shortest path algorithm. There's an example of special case of the shortest path algorithm in a graph like this where there's no cycles. And in the shortest path algorithm, you process every node and you do something. And the question is, what order should you process them in? And it turns out that one of the orders that solves a difficult version of shortest path is a breadth first order. So you need to use a breadth first search to get the ordering, and then the shortest path runs on that ordering. And that's typical of the kind of way breadth first could be used. There's a lot of more basic things breadth first search could be used for, like your Same game that you did last month and various other things like that, where you just want to process each node. OK. I'm not going to talk much more about breadth first search. I want to shift over to depth first search because it's more interesting. Here's a directed graph. I'm going to explain how depth first search works by showing you an example first, and stay away from the code and that aspect of it. That aspect's important, but I think it's better for you to get a sense first. So just look here. There's lots of examples of this in the book, and follow along. Depth first search picks a particular node to start at, typically the first node in the graph structure. Let's say that's A. And it visits things in a depth first order. Meaning instead of visiting all the children of A, it's going to go to the first child of A, and if that hasn't been visited yet, then it's going to do a depth first search on that node in a recursive way, thereby always going deeply first until it gets to a dead end. The normal thing you do as you do a depth first search is to store the tree as you go. So if I move from A to B, and I know that B has not been searched yet, because I look in my marked array, then I will put a parent pointer from B back to A. I will actually store my depth first search tree as I go along. A depth first search tree shows the finding of these nodes. That's one of the things that comes out of depth first search. We're going to use a depth first search tree in a second. The other thing that you might want to do is put numbers on the nodes as you find them. One number that you might want to put down is the order in which you first visited the node. The other number is the order when that node was finished with its depth first search. So I'm going to keep track of two numbers, one when it starts, one when it's finished, and the depth first search tree as we go. The depth first search tree, the parents point back, but I'm just going to darken them. The implementation would have a parent that points back, but I'll darken it. And the numbers I'll put next to each node with a slash in between. The left one being the number that we start at, the right one being the number that we finish at. You'll understand it right now because we're going to start. So we start here. At the beginning, all the vertices are unmarked. We haven't seen any of them. We start with this depth first search on A, so we mark it, and we mark it 1. We're going to keep a count. It's the first one we started. So we're starting A. After the slash, later on, I will put a number marking which, if it's the 8th, that's the 8th one that gets finished. It is going to probably be the last one that gets finished. So I won't actually mark this finished until I back all the way up and I'm done. This happens when I start my depth first search. The number here happens when I finish my depth first search. These numbers are used for very different applications depending on what you're doing. All right, and now I move to, let's assume that if we have a choice between children, it's always alphabetical, just to break a tie. So I'm going to move now to B. That is now in my depth first search tree. It's called a tree edge. There's a bunch of different types of edges that show up in depth first search. Something that moves to an unmarked node is called a tree edge. That's a tree edge. And it's got a parent array that's representing it someplace else. So the parent of B is now A. And now what's the start number for B? 2. And now we move on. Remember, A is waiting. When we come back to A, what's the next thing we're going to look at?
G.
G. Okay, but it's waiting. Now we're doing a recursion on B. Where do we go from B? C. Good. So that's a tree edge. And now C is 3. And then we go further deeply to D. That's a tree edge, and now D is 4. Now what happens at D? There's nothing in D. It's nil. D is now finished its depth first search. It is the first node whose depth first search finished. It gets a 1. These numbers have to be global or static variables. They cannot be stored at the different levels of recursion differently. They are above the recursive levels. Okay, there's just one set of numbers at all the different levels of recursion for the first number and one set for the second number. All right, now we go back to C, and C is finished. And now we go back to B, and B is not yet finished. So we go forward again. And E gets 5. Yes?
The part that you're symbolizing by drawing the lines in darkly, you say you're storing the trees, storing the pointers or whatnot.
We have a pointer array. The pointer of D is C, the pointer of C is B, the parent of E is B, the parent of B is A, the parent of A is nil. We have a parent array that is storing a tree to keep track of these actual tree that I'm constructing.
Okay. Now, on this next step, you're going to get to E, and you're going to see that D has already been seen.
Good.
So D is not going to get a parent of E, or E is not going to be the parent of D?
That's right. The only time you set a parent is when the thing was unmarked when you got there, or when you're going to start a depth first search on it. We are not going to start a new depth first search on D because D already has a number.
But a node can only have one parent.
Although it really does have two parents. I mean, it's the parent. D has both C and D are parents.
No, but not in our depth first search tree. D's got one parent in our depth first search tree. The parent of D is C, and it's going to stay like that. It doesn't change. Once you go forward to a node that hasn't been marked before, it gets a parent, and that parent stays fixed. So now we're going to check E to D. D is already marked. It has a number. So we do not add this edge to our tree, which means we do not change the parent of D, and we don't start a depth first search on D. And in fact, now we're done with E, so E gets the number 3 for the finishing time. Okay, let me stop. Any questions so far?
5, 3.
Got to remember where you're up to. It's always a little tricky. Where are we up to? Back to B, then B is finished, so it gets 4. Back to A is not finished. We move forward to G.
Is it at random? There's 2.
I'm deciding on them in alphabetical order. So G gets the number 6. And now we move forward to F. And that gets the number 7. And then we move forward to E, which is already marked. So now F is finished. And it gets the number 5. G is not finished. We go forward to H. And this gets the number 8. G is now finished because it's H is now finished, and it gets the number 6. G is now finished. It gets the number 7. A is now finished. It gets the number 8. So we've kept track of a lot of things. The depth first search tree by pointer array, the first find numbers, and the finishing time numbers.
So so your darkening of lines represents connecting parent pointers.
Right. The darkening of the lines represents connecting parent pointers. Now, in a depth first search tree, and this is just some lingo that you'll see in the book, so you should know what it means, every edge has a classification. The edges I darkened are called tree edges. They are the edges between nodes that we headed towards when they were unmarked. What would an edge like this be called? Remember, we were here, here, here. We backed up here, 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 and then we went over here. This edge is called a cross edge. It crosses from one end of a tree to the other end of a tree.
I thought it was a forward edge. I thought cross edges connected parts of trees that were different trees to begin with.
No, forward edges are edges that connect things. If you start from here and you move down here, a forward edge would actually go ahead on the tree, further down on the tree. I don't think that's a forward edge.
That's my understanding.
I could be wrong. You could be wrong, I could be wrong. Let's see if I can, here. See this edge? That's a forward edge. Because it connects to something that's already in the tree, which is forward on the tree. Let's see if we have any back edges. We don't have any back edges here because this graph doesn't have cycles. But if there was an edge, if we got to here and there was an edge back to A, that would have been a back edge. A back edge is something that points back up the tree. A forward edge is something that points down the tree. A cross edge is something that does neither, that connects different pieces in the tree that are neither up or down, like from here to here. I'm pretty sure that's right, but I'll double check it, Chris. And a tree edge is the ones that are dark. Now, it's terminology that is helpful because a book will talk about it, but I should just say one thing. When you're talking about a graph without directions on the edges, then there's only two kinds of edges: tree edges and back edges. There's no forward edges, there's no cross edges, because there's no direction. So either you got a tree edge or you got a non-tree edge, which is called a back edge. And the distinction between tree edges and back edges are the most important ones to make. You won't see much of an importance between the difference between a forward edge and a cross edge. But distinguish between tree edges and all the others is important. So the tree edges are darkened and all the other edges are things that hit things that were already marked before. And they might have been in different parts of the tree, and depending on where they are in the tree, they get a name. All right, let's actually do something interesting with this. And this will be the last thing. I think we'll finish up with this application.
Shai?
Yeah.
Just a quick question. So in contrast, the breadth first search isn't storing any sort of tree. It's just putting things on the queue.
The breadth first search could also store a tree. But in depth first search, the tree is really useful for so many things when we talk about it. And for breadth first search, it isn't always so useful. So, but you could definitely store a tree with breadth first search. Every time you take something, every time you hit something that's going to go on the queue, you store its parent pointers back to its parent. So you could also store a tree there, but it's just not as interesting. You can have a breadth first search tree too.
Are you going to give some examples of why we
Yeah,
do all this storage?
right now.
Okay.
Right now. Right this very second. All right, so let's use this to do an algorithm we did the very first day of graph algorithms, topological sorting. We're going to do topological sorting on this graph using this work we've already done. I've taught you how to do depth first search. We've done it. We've got all these numbers stored. We've got the parent things for this depth first search tree stored. Let's go ahead and use it to do topological sorting. The thing about depth first search is the way you use it is always so clever and slick that there's got to be a cool theorem behind it. And that's what happens here. We've got this depth first search tree. Let's go ahead, and I'm going to make this seem magical because I think it's cool, but then I'll explain kind of what's going on. Let's go ahead and take this tree and do a traversal of this tree in a fashion where we do the children first and then the root. Okay, what's that called? It's called post order. They're going to do the children first and then the root. The root comes at the end. What gets printed out first? The children first. So let's say alphabetical order again. We go this side. In order to print the children of this tree out, we go this side. So D, then C, then E. Let me write it out. D, then C, then E, then B. Now we got to go to the other side. F, H, G, and then back to A. If you read this from the right to left, it's a topological sorting of that graph. So if you do a depth first search, store the depth first search tree, do a post-order traversal of the tree, and read it in reverse, that's topological sorting. How long does it take? It takes you order edges time to do the depth first search, order n time to do the traversal on the tree, and nothing to read it backwards, just copying it over. So that's really cool. That's example one.
Could you review what topological search is?
Yes. It means that if you drew this graph in a straight line from A, B, G, then all through D, then all the arrows go in the same direction. But you get all the prerequisites before you get what they're going for. So A comes and then G. That's because we've gotten all the prerequisites for G finished. And then H is going to come because we've got all the prerequisites for H finished, etc. All right. This is actually not the actual normal way you'd use depth first search, but it's just a cool, nice way of thinking of it, so I like to show it to you. There's an easier way of getting the topological sort. And look at the finishing numbers here. The finishing numbers are exactly this post-order traversal. Everybody see them? 1, 2, 3, 4, 5, 6, 7, 8. They're exactly the same order that I just did this post-order traversal. I wanted you to see that connection. But if you've done the finishing times as you move along, and what's even better, when you get the finishing time, just print out that node in an array of that index. And then you don't have to do this tree traversal when you're done. You did it along the way. So where does the action take place in this depth first search? It takes place at the finishing time. Topological sort is an application that can be done with depth first search if you concentrate your action at the finishing time. When you get a new finishing time for a number, print the node and stick it in the index of some array with that number. You don't have to do all this traversal at the end. You can do it while you go down. Questions about that?
Just
Yeah.
depend on which node you start.
Sure it does. Sure. In fact, if you're going to do a topological ordering, you have to start at a node that has in degree 0. If there's more than one node within degree 0, you have to do another depth first search to start at the other one. And in general, this is a good point Neil brought up, a really good point. In a directed graph, it's possible to start somewhere, finish all your depth first search, and are you done? There might be some nodes that are left unmarked that you couldn't get to. In this example, you got to all of them. I made this example up, so it's all connected. But you might get stuck. So typically what we do in a directed graph is we take our depth first search. Here's what we do. We have a little loop that starts with 1 and goes to the number of vertices. And we tuck our depth first search inside it. What this means is you're going to start at the first one, at A. If you finished all through and there were some left, then you'll find it because you're in this loop. You'll go down to 2. The first thing you'll do is you'll see, oh, 2 is marked, so don't do it. So you need a little if statement. If unmarked I, then depth first search I. So then you start from the first one, you do all your markings, you go down to the second one. If it's marked, you skip it. Third one marked, skip it. Fourth one marked, skip it. Then if you have another node that was left empty, you'll start from that node. This does not slow down the complexity. This just adds an extra n. You're already taking e time. This just adds an extra n because you might have to go through a whole bunch of nodes that have already been marked and check that they're actually marked. But it doesn't add any extra to the asymptotic complexity because n is smaller than e. So when you do directed graphs, you usually stick it in a loop like this. All right, so that's a really good point, and you should know that. What if the graph is undirected and I stick it in a loop like this? It doesn't slow it down, but is it necessary? What do you think?
You've got to get everywhere. If it's a disjoint.
If you're able to, if an undirected graph, you can get everywhere, so it's fine. But Chris mentioned, what if it looks like this?
It's a graph.
Yeah, it's a disconnected graph, but I finished my depth first search and I think I'm done. I should really go down and check if there's any more unmarked ones. In fact, what if I had a big graph that's 2 million nodes large, and I want to find out what its connected components are? I don't know if it's one big piece. I want to actually identify which pieces, and then I'll run my little shortest path on each piece. What if somebody gives me a map of the world, and some roads don't connect to other roads? So finding connected components is actually a very useful thing to do, and it's really easy with depth first search. You just wrap your depth first search in this loop, and every time you finish a depth first search and you move on to the next I, you say, I found a new component and it's the second component. I found a new component, it's the third component. It's easy to do connected components just with an algorithm that looks like this. By the way, you don't need depth first search to do connected components. You can do connected components with breadth first search also, because there's no, anything you can do with the early numbers, you can do with breadth first search. If you need the later numbers, that's where depth first search comes out with its power. Okay, that's a general good rule of thumb. Okay, so this wrapping is important for doing various connected components. Depth first search is a cool idea if you calculate the finishing times. And there's one really nice example of this, topological sorting I showed you today. But there's a nicer example, the example of strongly connected components. And I'm going to go through that next time. It'll finish up the idea of depth first, breadth first search, and then we'll shift on to shortest paths.